Whether it's ChatGPT or Gemini or ArtStealer, it's no secret that AI is taking over the world. But I was wondering, how does it work? Turns out, most of modern AI is based on neural networks, an algorithm I'll be implementing today. Specifically, I'm gonna be making a digit classifier. Oh, and I also cannot use any library, so get this garbage out of here. This is a neuron. It has some entering weights, each representing a number, and an associated bias. Its value is the value of the neurons in the previous layers multiplied by their weights, with the bias added and all that plopped through an activation function. Why? Well, without it, the network would just be a line, and as we know, lines are garbage. Either way, this is the whole network, consisting of many individual neurons, with the input to the first layer being just an array representing the grayscale pixels of the image. Now, let's get coding. I implemented it in Python, so yeah. Most people use libraries like NumPy, but I'm too lazy to learn that, so I had to implement everything myself. Yeah, I get it, best practices, blah blah blah. Hence, I had to write a few utility functions myself. This function calculates the weighted sums, this one as the biases, and this is the activation function. Don't worry about the names, it's just some linear algebra garbage. Thanks to them, the front pass is just this short, wonderful snippet. So, are we done now? No, not exactly. You see, the weights and biases constitute something called parameters. They are not set, but they need to be learned. Wait. Before we even get started on that, we need to be able to grade the network. Consider this network. It receives some input data, does its networking and returns something. We also know that expected output, and from this, we can calculate the loss, aka the mark. I'm using mean squared error, so the loss is the sum of the differences between the respective values squared. When training, we work with fixed samples and variable parameters, so the domain of the loss function is usually just the weights and biases. But with all of that out of the way, we can finally get to training, which is done with... oh... yeah. So the formula is kinda complicated and I ain't explaining the formal bullshit, but quickly. Imagine a simple network with just one weight and a bias. Then, the loss is a 3D function that we can visualize as a hill. The weight and bias determine your position on the hill. The reverse delta represents the direction of the steepest ascent. This shortens and reverses it, and this means you do it iteratively. Oh, and yeah, this also has many bottlenecks, like local minima and optimizations, but look, I ain't a mathematician, so I'm not explaining it. I implemented it like this, and ran the program. Yeah, it's too slow. To calculate the gradient blazingly fast, we use an algorithm called backpropagation. For clarification, I've tried implementing this algorithm twice before and failed. But this time, against all odds, I finished! Yay! So, are you like, gonna explain it? No. Suffer. But seriously, this video would be like an hour long if I were to explain it. Look, I'll link some resources in the description. Now, we could start implementing the classifier right away, but I prefer to test it on the XOR test. That's the function from digital electronics, isn't it? Yes! In AI, it's used because, well, let me plot all the Boolean functions on a graph. As you can see, all other functions can be separated by a line, and as we've established, lines are garbage. Except for XOR, which tests the network's ability to deal with nonlinear problems, which basically means the dataset cannot be separated by a single line. Who would have guessed that? This is the last explanation of the video, and it's time for the gruesome task of designing the network architecture. I eventually figured out this architecture and the learning rate of 0.2. And I'd rather not talk about how long this took me. Okay, let's finish up with the digit classifier. I stole the architecture from 3blue1brown, tested it and failed. After a minute of googling, I discovered that I should have normalized the input, basically turned the array of grayscale values in between 0 and 1. Running this yielded those results. And I'd say, good enough. And if it's not good enough for you, well, your opinion doesn't matter anyway. So, thanks, bye.